Hello, everybody, and welcome to today's webinar on Amazon SageMaker RL, where we're going to learn how to do reinforcement learning at scale. I'm Urvashi Chaudhary, Senior Product Manager, Amazon SageMaker, and I'm joined by Vineet Khare, Manager, Applied Sciences in Amazon SageMaker. Let's first start by understanding the various machine learning capabilities in AWS. Our goal is to put machine learning in the hands of every developer and data scientist. And as you can see, our capabilities can be divided into three layers. At the very bottom, we have a great selection of frameworks, interfaces, and the latest hardware that you can use for machine learning. In the middle, we have a fully managed platform for machine learning, Amazon SageMaker. And at the very top, we have services for various machine learning areas such as vision, speech, language, chatbots, etc. Today, we'll be focusing on Amazon SageMaker and reinforcement learning, which was launched at reInvent 2018. Amazon SageMaker is an end-to-end machine learning platform that helps you build, train, and deploy machine learning models at scale. If you look at the machine learning process, it starts with you collecting data and preparing training data, picking the right algorithm and optimizing it, setting up your training environments and doing the training as well as tuning of your machine learning models. Then deploying these machine learning models in production so you can serve predictions, and then being able to scale and manage these production environments so that your retrained models can continuously be deployed. So Amazon SageMaker supports this end-to-end machine learning platform with various managed capabilities. For collecting and preparing training data, we have pre-built Jupyter notebooks that come pre-configured with the environments and infrastructure that you would need. We also have Amazon SageMaker Ground Truth, a service that we launched at reInvent 2018 that helps you build label data sets at 70% or more cost savings. In order to help you choose and optimize your machine learning algorithms, we have a selection of various built-in algorithms that have been optimized for giving you better performance. We also have an AWS marketplace where you can buy pre-trained machine learning models or algorithms from various sellers. Once you've built your machine learning model or decided which one to use, we enable one-click training on Amazon SageMaker, and it's a fully managed environment where we take care of setting up your training clusters as well as tearing them down when your training is complete. So you can run distributed training at scale in a very cost-effective way. We have several model optimization features such as SageMaker Neo that helps you train your model once and then optimize and compile your models to run on various different device targets with 2 times or more performance improvements. We also have automatic model tuning in Amazon SageMaker that automates the process of hyperparameter tuning so you can accelerate your machine learning training process. And once you have your trained models, with Amazon SageMaker, you can do one-click deployment to either the cloud, so you can serve predictions in real time and low latency, or you can deploy your machine learning models to run batch predictions on large amounts of data sets that don't require low latency. You can also take these machine learning models and deploy them on the edge through AWS Greengrass. And we also have several managed options for managing your infrastructure. So we have auto scaling that you can apply so that your hosted endpoints can serve traffic and can manage the ebbs and flow of traffic in production. And as you can see, we have several key customers using SageMaker in production today. So let's focus now on reinforcement learning, or RL. We're very familiar with the two common machine learning techniques, which is supervised learning and unsupervised learning. With supervised learning, we typically provide a labeled training data set, and the machine learning models learn how to apply predictions based on the labeled data set that it has been trained on. With unsupervised learning, the machine learning model detects patterns in the data, and it doesn't require a pre-labeled data set. It understands the patterns, and then it can match predictions for new data based on the patterns it has already learned. With reinforcement learning, we learn by interacting with the environment. And typically, the learning happens over multiple trial and error. And the goal here is to optimize for long-term rewards. And the goal is to learn strategies that can help maximize for this long-term reward. And over time, the RL models can learn how to make complex decisions. So it may seem a little new and different, but through this webinar, we'll peel back the layers and we learn what reinforcement learning is, as well as how reinforcement learning is accelerated in SageMaker. And we'll also dive into some examples. The new concept here that we are working with RL is an RL environment. And an environment is simply a representation of the real world. It's pre-programmed to represent real-world conditions and mimic the interactions that a user or a computer program would have. And it's dynamic and it can update itself based on its program behavior. A simple way to think about an environment is it's a way for your RL models to learn and train from. So if you were to learn how to fly an aircraft, typically you wouldn't start by flying an actual airplane. You'd start off by learning in a flight simulation, and that flight simulation mimics the conditions that the actual aircraft is in, so you can learn in a safe environment. Similarly, when you are training robots, for example, to do certain tasks, or you're training your autonomous vehicle to run autonomously on the roads, it's unsafe or expensive to do this on the actual robots or autonomous vehicles. And so we start off by learning in a environment. And this ability for RL to interact with an environment and learn through its experiences and make long-term complex decisions makes it applicable in several domains, and not just gaming, where we already see several RL applications. So some examples would be robotics, industrial control, HVAC systems, autonomous vehicles, as well as other areas where currently we may be using dynamic programming, so areas around resource allocation or capacity planning operations, as well as dialogue systems or customer engagement use cases where you want to decide when's the right time to send a notification to a customer and what content you should recommend, and so on. And RL is applicable in all of these domains because it's optimized to achieve outcomes and not just take single decisions or predictions. So I'm going to hand over to Vineet now, who's going to talk to us about the basics for reinforcement learning.
Thank you, Urvashi. So before we talk a little bit more about the SageMaker RL features and look into some of these examples in more detail, we'll start off with some of the key concepts using a very, very simple example. We're going to use the prototypical example of a cart pole, where the task at hand is that we are trying to balance a pole on a cart by moving the cart left and right. So the the state for this particular problem is defined as the position and velocity of the cart and position and velocity of the pole. We also talk about an agent or a policy which takes actions in this case. So the actions in this case is either go left or right. So the input to this agent or policy could be the state, which was defined by the 4 parameters, and the output is a binary decision left or right. And as is demonstrated in this particular slide, this policy could, for example, be a neural network. The RL environment that Urvashi mentioned earlier, in this case, is defined by the system dynamics, which in turn is governed by the laws of physics such as friction and gravity. So what happens is at every time step, the current state as well as the action from the policy goes into the RL environment, and what we get out of the environment is the next state and a reward. I'll come back to how this reward could be defined, but this iterative process of what we call stepping through the environment generates data of this form, which is the initial state, the action, the next state, and the reward. So essentially what we're trying to do here is to learn a policy that can control this cart such that the pole is balanced on the cart. And this policy maps the state to an action. And the objective here is to maximize agent's long-term reward. And how is this reward defined? So again, let's take a simple example. Let's say at any given state, the pole is up and we take an action to go left. Again, the pole stays up. We take another action to go left, it still stays up. And then we take another left and then it finally falls down. So one way that we could define the reward for this particular problem could be based on whether the pole is up or down. So for example, we can say that whenever the pole is down, we get a reward of 0. And whenever the pole is up, we get a reward of 1. But how an agent is doing at any given state not only decides what happens in that state, it also influences what happens down the line. So what we do is we do a cumulative discounted sum of rewards. What does that mean? So we pass the rewards back to the upstream states using a discount factor. So for example, in this particular case, if the discount factor is 0.1, I may get these rewards for the first 3 states. In terms of the algorithm itself, there are a few algorithms that we can use to learn the strategy that can help the pole to be balanced on the cart. But we are going to talk about a very simple algorithm called the policy gradient algorithm. What this algorithm does is it maintains a stochastic policy which is used to sample the actions. And initially, you start off with random weights. So for example, if we had the neural network as this policy, we start off with random initialization of that neural network. We run through 100 or so episodes. And an episode in this case is defined by a sequence of actions during which the pole is up and it finally falls down. So we generate, let's say, 100 such episodes within the simulation environment, and that generates the training data. And this training data then is used to calculate the gradients for every decision that was made by the agent. And finally, as we would do in any gradient descent algorithm, we would update the weights using the gradients calculated in the previous step. The only difference here is that unlike supervised learning where we have labels, in this case, instead of labels, we have these cumulative discounted rewards that we use. So again, I'll not go into a lot of detail of this algorithm, but a couple of key concepts that I should mention in passing, which are important here. So if we continue to take the actions that the policy is suggesting, there is a chance that we get stuck in local optima. So many a times the strategy that we follow is of explore exploit, where a certain percentage of the times we take random actions. And the other concept here is what we call experience replay, where the training data is being generated within the simulation environment, and it is being used to train at the same time. So it gets stored into a memory data store and it gets selected from. So I'll now hand it back to Urvashi to talk about some of the other SageMaker RL features.
Thank you, Vineet. So with the basics concepts of RL that Vineet has just covered, let's see how we put those into implementation and see an example of how we can use RL in SageMaker to train our humanoid, Harry, how to walk. So as mentioned earlier, our goal is to maximize long-term rewards. And this is a graph that shows the how across multiple training episodes the rewards look like. And it's important to note here that initially the rewards are negative and they are slowly starting to get better over time, and around the 1,000 episode, you can see that they are fairly flat. So this is important because initially your RL agents will take some random actions to try to learn from different explorations that they're doing. And those experiences over time result in incremental improvements in your policy that then get better over time to provide consistently better reward. So let's see this in action. So as we talked about earlier, we start with an initial model and we interact with an RL environment. So here, Harry, we're teaching Harry how to walk, but right now, Harry can't even stand up. But all this data that is being generated from the interactions here as Harry tries to stand up in different ways is instrumental because these actions and observations slowly contribute to developing our learning policy. And you can see that slowly Harry starts learning how to balance, so he's not falling as quickly as we saw in the earlier iteration. But Harry still can't balance and still is not able to walk. So the actions, observations, along with the rewards are stored as training data and passed back to SageMaker training. We retrain the model and then these updates are sent back to interact with the environment. And you can see that we are slowly starting to learn from the actions that had happened earlier that resulted in negative rewards. And Harry is learning how to increase the rewards that are being given by the environment and is able to now stand and slowly step, but still not able to walk. And if we do this retraining over multiple episodes, you can see that slowly Harry starts making progress and is able to walk. And over time, you can see that we've trained Harry how to walk. And you can continue to take this forward by training your RL models how to jump obstacles and play games and dance and so on and so forth. And throughout the training process, SageMaker RL enables you to visualize your training. So in this case, we were visualizing the videos, which are very helpful to understand how the learning process is happening, as well as various metrics. And once you have a model that you are comfortable with and you have a trained policy, you can take that and you can deploy it onto your actual device. So in summary, RL models are learning how to make decisions to accomplish tasks. So here the task for Harry was to walk across a field, and in your other cases, your decisions might be how to allocate certain capacity or how to navigate a autonomous vehicle across the street and so on. But what we found from talking to customers was that training RL models is tricky because there are some key challenges with running RL workloads. First, it's difficult to get started, and these RL agent algorithms are complex and less known than some of the other supervised and unsupervised learning algorithms. The new variable with RL is the RL environment, and it's hard to integrate that RL environment with your existing training infrastructure. In addition, training can be computationally expensive and time-consuming because we saw that it requires frequent trial and error, and you need to frequently tune your hyperparameters as well as your RL environment. And so with SageMaker RL, our goal is to make RL accessible so that any developer and data scientist can quickly get started with RL and run RL workloads at scale. And the way we do this is by providing various pre-built environments for RL, so you don't have to worry about the infrastructure setup or the libraries and dependencies to get started with RL. And we have 12 examples, and we're constantly adding more on how to apply RL for different problems using different types of algorithm choices and frameworks and toolkits. We've incorporated and integrated the most popular and state-of-the-art RL agent algorithms in SageMaker RL, so you can simply select a specific algorithm and get started quickly, as well as we have common interfaces for integrating various types of simulation environments. And the platform provides a fully managed and robust capability for running various types of RL workloads. So SageMaker RL enables you to train RL models using state-of-the-art agent algorithms. And the way we do this is that we've extended our built-in TensorFlow and MXNet frameworks to support popular RL toolkits, namely RL Coach from Intel and RayRL from Berkeley Rise Labs. And these toolkits have implementations of some of the most popular RL agent algorithms that you can simply select and get started with. Similar to how you would do supervised and unsupervised learning in SageMaker, we also have the ability for you to create your own custom environment for running RL. So if you'd like to use a different framework choice or use a different RL toolkit or algorithm, you can always bring that in through your custom developed container and run it in SageMaker RL. And we enable you to connect to various RL environments because the interfaces for SageMaker RL for connecting to environments is through the OpenAI Gym interface. And using that, you can connect to AWS simulation environments, namely AWS RoboMaker, which was a new service that we launched at reInvent 2018, as well as Amazon Sumerian. You can connect to open source environments such as Energy Plus for HVAC applications and RoboSchool for robotics applications or any other open source environment that you may wish to use. You can even build your own custom environment, so you can code this up in Python or a different language of your choice and bring that into SageMaker RL and connect your RL model and train using that environment. And lastly, you can also connect to commercial simulation environments such as MATLAB and Simulink if you're doing some controls or manufacturing type use cases where you're building and using commercial simulators. And SageMaker RL as a platform provides robust capabilities to run production workloads using RL. So we have the best options available in terms of hardware choices that you can use. You can do single machine training where your simulation and your training is happening on the same machine, or you can distribute this over multiple training nodes or through over multiple machines. Your simulation environment that you connect for training could be a local environment, or you could use a remote environment, as well as you have the logging metrics and visualization capabilities that you can use to make sure that your training is satisfactory and you know where you want to tune your models. The SageMaker automatic model tuning capability, which applies machine learning to do hyperparameter optimization, can also be used with SageMaker RL, so it can accelerate how quickly you can try various hyperparameters for your RL agent algorithms and accelerate your overall training time. And lastly, we have the capability to run homogeneous or heterogeneous clusters. So this is very important, where your training can be run on GPU machines, which are very powerful and can accelerate the training time. And you can connect to various CPU machines for doing your simulation or running your RL environments. And this helps not only scale out your RL workloads by parallelizing your simulations, but it also gives you a very cost-effective option where you no longer need to also use GPU instances, for example, to run your simulation, because these are more compute heavy, so you can optimize your cost by running the simulations on the CPU machines versus having to run on GPUs. And so this greatly reduces the cost for running RL workloads and enables you to run large production scale workloads in AWS. So let's see how SageMaker RL is used to train AWS Deep Racer, which is a fully autonomous 1/18 scale toy car that we launched at reInvent 2018. So here you can see that we are using AWS RoboMaker as the simulation environment and training the Deep Racer on various track types, configurations, lighting conditions, starting points, etc. And this is helping parallelize the training and accelerate how quickly your RL agents can learn. So with this, we've learned how SageMaker RL works. We've learned about the basics for reinforcement learning, and we've looked at some examples. Let's now hear from Vineet and dive deeper into how SageMaker RL can be used to train other types of applications and how you can build your own RL models.
Thanks, Urvashi. So for the remainder of this webinar, we are going to look at one particular example using SageMaker RL. But before I go into that, I want to point to the set of examples that we have in our GitHub repository. And I'll use one of the diagrams that Urvashi earlier used as a point of reference. So in this particular architecture, you have this SageMaker training box and you have this RL environment box. So essentially all the examples that we have in the GitHub repository showcase a mix of different deep learning frameworks, reinforcement learning toolkits, and environments. So very quickly, here is a link to the GitHub repository, which has all the examples. And if I point out to a few of those, the Deep Racer example that Urvashi briefly mentioned, that one uses TensorFlow as the deep learning framework, Intel RL Coach as the reinforcement learning toolkit, and AWS RoboMaker as the simulation environment. The HVAC example uses MXNet and Intel RL Coach as deep learning frameworks and RL Toolkit, and Energy Plus as the simulation environment. Similarly, there is another example which is used to compress neural networks, and that one uses TensorFlow, Ray RL Lib, and a custom environment. The example that I'm going to cover in a little bit more detail is the predictive auto-scaling example. And this one uses TensorFlow, Intel RL Coach, and it also shows how you can bring your own environment and use it with SageMaker RL. So before we jump into the example, a few pointers about the example. So while it is a toy example, it demonstrates how you can build an auto-scaling system which responds to different workloads by adding or removing servers. And the load itself is simulated in this case with certain variations and occasional spikes. And the environment that we have coded up with this example uses the OpenAI Gym interface, and it implements different steps. At each step where you can either add or subtract servers, you can, so whenever you add servers, there is additional time that is needed for the addition and additional costs involved because you're using more machines. Subtraction reduces the cost, but it happens at the expense of the capacity that you can process. So while I'm going through this example, more details about this examples are also published in an AWS blog, the link to which is in the slide. So the simulated load, like I said, it is nothing but simulated transactions per minute over a 3-day period. It's mostly periodic and with a few sharp, unpredictable spikes. This is typically what you would expect in a real-life scenario as well. Amongst many other things that you need to think about when you're trying to write your own custom environment for training RL models, you would need to think about how you want to define your reward function. We looked at how this was done for the cart pull example earlier. In this particular case, what we are doing is we are defining the reward function such that for every successful transaction that we process using the auto-scaling system, we get a positive reward out of it. Anytime there is a downtime, there is a high cost for that, so negative reward. And there's also negative reward because of the machines that we use, so because of the cost involved in terms of using those machines. So before I move on to the actual demo, this is a list of all RL examples that we have. Earlier, I pointed you to the GitHub repo. When you open a new SageMaker instance, you also get these examples by default. The only thing that you need to do if you wanted to, say, for example, run the predictive auto-scaling example is to go here and then say use. So at this point, I'll switch over to the demo. And like I said, this is a Jupyter notebook which starts off with some context to the auto-scaling problem. Since I've already covered this, I'll not spend too much time on this. It talks about the problem statement as what is the objective, how the environment is defined, what is the state, and so on. So you start off with a few prerequisites in terms of the import statements, in terms of the S3 buckets where the data should be stored, in terms of defining a variable name that we can use to track the training run. So there are a few other features that this particular notebook highlights, in particular the local mode feature, which will let you train the RL model on the SageMaker notebook instance instead of remotely. And that typically helps if you're trying to iterate through different experimentation very quickly. But for the lack of time, I'm not going to go into the details of the local mode in this particular webinar. So there is an IAM role that you need to define that we'll use for training. Again, skipping the parts related to the local mode. The notebook has the sufficient level of detail in terms of description as to how you can use the local mode. So if you're interested, you can go back and look at it. So now coming on to the environment itself. So as I said earlier, this involves writing the gym interface. So typically, this is a set of functions like initialization, step function, which, like we saw in the cart poll example, takes a state and action and returns in the next state, and a reward, reset function, and in some cases, if rendering is relevant, a render function. So since I've already covered the reward definition in a little bit detail, I'll not go through this this file, which autoscales sim.py, which has the environment definition in it. You can go back and look at it in more detail offline. So now let's look at some of the loads, simulated workloads that we have generated. So again, a few cells that plot this here in the notebook so they can visualize how the workloads are looking. So a few of them we have plotted here. So some periodicity with occasional spikes which are difficult to predict. So once we have the environment and the simulated workload defined for the example, we look at the RL algorithm that we are going to use to train the model. And in this particular case, like I said, we are using Intel RL Coach, which has a suite of algorithms that you can use. And this particular example, we are using the PPO algorithm. Again, you can go back and look at this particular file, which is called the preset autoscale ppo.py, which has all the configurations needed for training, such as the number of steps, such as the learning rate, such as the batch size, and so on. So moving on, the training code itself, again, there are quite a few functions that I can go into the detail here, but one particular function that I would want to highlight in this case is this one called map hyperparameter. So what does it do is you can use it to configure some shortcut names for the hyperparameters that you expect to change frequently. So if you are experimenting with, let's say, learning rate, this could be one of the parameters. So the idea is there are a whole bunch of parameters that are somewhat static, and there are a few that you want to experiment with. Using this function, you can override those parameters with values that you specify in the estimator. So I'll show an example of this a little later, but moving on. So this is the part where we actually execute the training command. So the RL estimator, which is the part of SageMaker Python SDK, lets you define an entry point for the training file. This is what I showed earlier, train-coach.py, source directories, other which contain other files which are relevant for training, a toolkit, which is coach in this case, framework is TensorFlow. You can also define the training instance type. So you see we are using m4.xlarge here. And in order to distribute the training, I can specify train instance count to be more than one here. Again, some settings related to the S3 path and so on. And here is where we are overriding the parameters. So while most of the parameters are being consumed from this preset file that I showed earlier, some of these can be overridden here with specific values from the estimator itself. And once you have defined this, all you need to do is you just need to call the fit function on the estimator. As Urvashi said earlier in her presentation, visualization is very important, especially for long-running reinforcement learning jobs. So What we do is we provide a functionality that enables users to uh, access the data that gets generated during training as the training is going on. So if, let's say, your reinforcement learning training is generating certain videos, these will get copied to a certain S3 location, and you can go and look at the videos to see how the training is progressing. Similarly, you can look at, let's say, different metrics like the reward function as to how it is progressing. And based on that, you can decide what you want to do in terms of either a different parameter selection or stopping the training or continuing with it. So you can store intermediate training output and model checkpoints with SageMaker RL. And in terms of visualization, like I said, you can plot. In this case, what I've done is I've plotted training reward as a function of the episodes. Since many of these RL examples we train with a simulation environment, many a times evaluation can also be done within the simulation environment. So what this notebook shows next is how you can load a checkpoint that was generated during training and just evaluate it in the simulation environment without the model training part. So if you do that, you'll get the aggregate reward value for the number of steps that you ran the simulation for. So this is the evaluation step. Again, what we do is it's nothing but a SageMaker training job, except for the fact that training only involves the simulation run with the trained model. So again, most of the parameters are same. The entry point here is the evaluate coach.py. If you go and look at this file, you'll see that it only has evaluation steps in it. And I specify the checkpoint location here to tell the evaluation step as to what model should be used for evaluation. You can also host these models. So in this particular example, just to showcase how you would do that, you can use the SDK to deploy this model with a certain type of instance and certain count of instance that you want to host this model with. And then once you have hosted this model, you can also infer using the hosted endpoint. Again, in this particular example, because this is a dummy example, we've used the observation to demonstrate how you would infer against the hosted model, but you could, for example, change this particular cell to specify the payload that should be used for inference. And finally, once you're done with your model, using the model for inference, you should delete the endpoint. So switching back to the slide deck that I have, I want to end with this summary slide, which tries to capture all the features that SageMaker RL has in terms of it being fully managed, in terms of it being able to support a wide variety of deep learning frameworks and RL toolkits, and support for different environments for RL training. And with that, I would like to thank everyone for their time, for joining us for this webinar. Thank you so much.